Hello, wonderful people of the internet, and of course, MIT Class 18S191 on computational thinking. Today, for this little mini lecture, we're going to talk about something that is slightly tangential to the main climate saga that we've been going through for the main lectures. And instead, we're going to talk about how these climate simulations are run in practice. And the answer is that they're typically run on supercomputers. So what is a supercomputer? If you're like me, I naively thought that supercomputers were just supercomputers. They're normal desktop computers that are really, really, really strong. But when you think about it, we're kind of pushing the boundaries for what we can actually put into a normal desktop computer. So what exactly makes supercomputers fast? And how exactly do we tell how fast they are? That brings me to the main point of today's lecture. Can supercomputers run Crisis? That is to say, if you wanted to play a video game on a supercomputer, how exactly would you do that? And would it even be a good idea? And the reason I specifically want to talk about video games is that, well, when you think about benchmarking classical desktop computers, usually you think about video games. You think about maybe playing a game and seeing how fast it is, how many FPS you can get. In fact, there are a bunch of really cool benchmarking sites out there, like for example Phoronix, that do precisely this. They give you, first of all, what they expect the hardware to do, and then they give you real-world scenarios of that hardware running in practice by playing different games and seeing how fast those games are. And one big famous game for this a few years back was Crisis, which is why it's still kind of a bit of a meme in the community. So, supercomputers are fast, but can they run Crisis? Is that even a good idea? That's the next question that we're going to tackle by talking about what a supercomputer is in practice. So I'm going to draw a little box over here, a little yellow box, which basically corresponds to your own personal computer or PC. The idea is that this computer has a CPU associated with it along with a GPU, and the CPU has some number of cores, while the GPU also has some number of cores. And we've talked a lot about naive parallelism on this one desktop device. We've talked about how to use the GPU, how to use the CPU, and it's important to know how to do that. However, a supercomputer is usually one step of parallelism beyond that. Instead of just parallelizing within your own machine, you instead have this entire network of machines, which are all basically just as powerful as your normal computer. So all of these guys are basically the same strength as your individual PC. In fact, it gets even more weird than that, because some of these, for example, maybe this group here, could be specifically focused on GPU computation, that is general purpose graphics processing unit computation, which is really taking over the high performance computing scene nowadays. And maybe this group is just your general compute nodes, so it's focused on CPU computation. And so the way supercomputers work, the reason they're so fast, isn't necessarily because each individual node is fast, but because as you add all of these nodes together, all of these individual PCs together, you start to get something that is much faster because you can make use of that parallelism. Now, we've already talked about some methods that can't really make appropriate use of parallelism, but a lot of things in specifically scientific computing can really use a high-performance computer or supercomputer to its full potential. So how exactly do you go about using this machine? Well, you use it by having yet another little box in here. And this is going to be your login node. It's the thing that lets you access all of the rest of the compute resources on the compute cluster. So you'll go from your PC to the login node via some software, usually like SSH, which is called the secure shell. The idea is that you take your terminal and you use SSH in order to log in to some terminal available on some compute node, which can then access any of these nodes, in fact, more than one node at a time. So let's focus on this element here. How exactly do you go from the login node to the CPUs and GPUs to do all of the really heavy computation that you need? This is via something known as a scheduler. Now, what the scheduler does is it basically takes any unit of computation that you send it, and it finds a time slot where it can actually do the computation. For example, let's say you need 8 nodes to do some computation for 8 hours. Well, we might not have those 8 nodes available now, but we could maybe in 4 or 5 hours. So what the scheduler does is it takes that code and it knows how long you want the code to run for, and it fits it into some time slot that allows for it to run maybe overnight or something like that. So if you know the code's going to run in 8 hours and it's going to take maybe 4 hours to find a slot in the schedule, then you know by sometime tomorrow you're going to have your code finished. And that's kind of the idea behind how people run supercomputers. They don't usually run it interactively, although it is possible to do so. Instead, they find some sort of time slot that will allow for them to run their code. Now, as a very important point, there is a little bit of latency between each of these nodes in here. That is to say, as these nodes start to talk together, it's actually a little bit hard for them to see each other. Though they can see everything inside of their node pretty well, it's hard to talk between these nodes, and so you're going to have to use some sort of message passing interface to send information between the nodes in an efficient manner. And even then, it's going to be the slowest part of your computation. So a lot of the times when you're writing code for supercomputers, you're trying to do your best to minimize communication between nodes. And that's really important, especially when we go back to that question of how do we run a video game on the cluster? So the first thing to note is we have multiple layers before we actually get to the nodes that we want to do the computation on, right? So if you want to play Crisis, if you want to play any video game on there, these nodes over here, well, they're probably good enough to run whatever game you want, right? The GPUs are top of the line, as are the CPUs, so if you just used one individual node to play your game, it would probably be pretty fast. So let's say you scheduled some time on any of the compute nodes in order to do your gaming session, right? Well, okay, this actually has another layer of complexity added to it that we didn't even talk about, and that is the fact that basically this entire supercomputer is a server that runs headless. That is to say, it's not usual that you're going to send graphical information from the compute nodes back over here to the login nodes. In fact, in most supercomputing clusters that I've used, this idea of sending graphical information from the compute node to the login node is explicitly forbidden. But let's say it's not forbidden. Let's say you can send information from the compute nodes to the login node. Great. Okay. Then you have the latency between the compute nodes to the login node, and again, network latency from the login node to your own computer. And because of this, if you're going to play any game, or in fact open up any GUI on a cluster, it's usually going to be pretty slow. Now, as I was talking about this on Twitch, some people brought up the idea of Google Stadia, because essentially this is what Google Stadia does. It has some large resource of compute or gaming nodes available. And the idea is that you can play the game on their servers so your hardware doesn't have to be particularly strong. And that's a great idea in principle. If you can minimize this network latency and you can minimize the data transfer between the CPUs and GPUs doing the computation or the gaming and the login node, you in principle could create a server that could allow you to do gaming really, really fast. But that's typically not the case for most supercomputing platforms that are out today, even though it could exist in principle. Okay, so there's one last ditch effort that you might go about trying if you really, really want to run a video game on a supercomputer. And that is that you might try to run the video game on the login node. And let me tell you, that is an awful idea, because this login node is not only used by you, but in fact maybe hundreds of other people at the same time. So first of all, it won't be particularly strong, and second of all, you're going to be using the computational capabilities of the login node for pretty much everyone else, and a system administrator is going to come by and get really angry at that. So do your best whenever you're running stuff on a supercomputer to make sure that you schedule it in advance with whatever scheduler is available at the time, read the documentation to learn how to use it, and use it properly. With all that said, I hope I've explained why playing a video game on most supercomputing clusters is pretty much a no-go, and if you want to benchmark how fast a supercomputer is, probably you should be going with gigaflops or something like that, instead of going with how many FPS you can get on a particular game. Okay, so that's all I wanted to say for this kind of high overview lecture, just explaining how a supercomputer is different than a classical computer. On Thursday, we're going to come back and we're going to talk about the history of climate models and talk a bit about the software engineering behind them, with a particular emphasis on how exactly we are supposed to write code for a system that is so drastically different than the computational system you have on your desktop. Thanks again for watching, and hopefully I'll see you next time.